Hello and welcome. Thanks for taking time out of your day today to take a moment and hear what I have to say about the latest developments of the Klingberg Wing Mark II. As you probably already know, I'm Reynold Klingberg, your host, and I'm here to explain what's been going on with the project recently as we've run into some very interesting aerodynamic phenomena and the efforts to help understand and explain the phenomena that's occurring and what we can do to accommodate that phenomena and make the glider fly better. If you've been following along, you've probably become aware that there are some significant controllability issues with my wing. Totally different than my original wing. This one, very stable, seems to have a really nice glide, but gosh, you just can't turn the darn thing. We've had a lot of problems with flow separating off of the elevons, and when that happens, you lose your ability to turn, and it's been causing some severe adverse yaw problems, amongst other things. And we've run through a gamut of fixes for the problem. We started out by sealing the elevon gaps. That did essentially nothing. We've tried trip strips in front of the elevons to try to trip the flow and keep it attached. It finally came down to the point where I had to bite the bullet and say I was going to increase the size of the elevons and stretch them out to the wingtip, which I really didn't want to do, but I felt I had to do it. As you may recall, one of the concepts of this design is that there are no control surfaces on the outer wingtip panels, and that's to ensure that they're always flying and help prevent stall spin accidents. Concept, as far as I know, has never really been attempted or analyzed or studied in the past. But flying wings are notorious for stall spins, and if we can eliminate them, that would be great. One of the main reasons for this project was the problems that I had with my first wing with stall spins, and I said, if I'm going to do this again, I'm going to solve that problem so I don't have to worry about that anymore. And having no control surfaces out in the wingtip panels was one of the concepts I was going to work with to prevent those stall spins. And it turned out that worked out great on the model, not so good in full scale. The flow was wonderful on the models, not full scale. You would deflect the elevon down, you get much past 14, 15 degrees, and the flow would separate. And on the model, I needed somewhere around 25, 30 degrees of deflection in order to get enough control authority over the wing, given that the elevons were mounted significantly inboard of the wingtip. Not unexpected, but it worked great on the model. However, on the full-size one, a lot of flow separation. Now, usually the difference between models and full scale in terms of flow separation has to do with Reynolds number. Some of you may be familiar with Reynolds number already, some maybe not. But Reynolds number lies at the core of the problems that I've been dealing with and trying to correct or improve upon. So I'm making this rather long video. It'd probably be the longest one that I've made out of all of them. We could run a couple hours here. I don't know where it's going to end up, but I know it's got a lot of segments to it. It's going to be long. So for my regular supporters, my patrons, I will issue those in segments as I finish them. And for you YouTubers, you'll just get one big honking video, and you might have to split it up yourself or go get snacks and scones to hear the whole story, because it is extensive. And in the past, I've tried to avoid bringing any kind of mathematics into the videos. It can put off a lot of people. They look at equations, they don't mean anything to them. And I've tried to put everything in layman's terms, and that is not a derogatory statement in any way. We'll say that people that are not highly educated relative to aerodynamics, and I would even go to the point of saying there might not be anybody in the world that's highly educated in aerodynamics, even though they think that's what they do, because it's such a dicey, unknown field. There's so much we don't know. we'll say that being an aerodynamicist is as much black art as it is science. So everybody's a lay person when it comes to aerodynamics. So to explain what's been going on, I'm going to have to get into the Reynolds number issue, and that requires that I put up an equation and talk about what the Reynolds number really is. And conveniently, I have that on a whiteboard here because I prepared a little bit ahead of time. Oh yeah, I wanted to say, because this is going to be so long and take so many segments to record this, please expect the fact that my personal appearance is going to change a lot. I'm going to have different clothes. I might shave for the next one. Who knows? But I'm going to squeeze them in wherever I can and eventually assemble it into one video. So here we go. Reynolds number. What is Reynolds number? Reynolds number is a non-dimensional number that describes the flow conditions and helps determine or helps define what the flow conditions might be. Very, very low Reynolds numbers will be laminar flow, and higher Reynolds numbers are turbulent flow. And the Reynolds number is involved with boundary layers, and we're going to discuss boundary layers a little bit later. But here's the basic equation for Reynolds number. The Reynolds number is equal to the velocity, and you'd go, gee, Raul, that's a U, not a V. Why are you using a U for velocity? Well, that's because we have nu down here, which I'll talk about in a minute. And when you write the Greek letter nu, if you're sloppy about it, it looks like a V, and then we get confused over what the heck we're talking about. So you use a U for velocity here. The length here is a characteristic length. For pipes, that would be the diameter of a pipe. For airfoils, it's the chord length of the airfoil. And the chord length of the airfoil is from the point furthest forward on the airfoil, the leading edge, all the way to the trailing edge, and it's a straight line drawn between those 2 points, and that would be the chord length. And nu here underneath, that is the kinematic viscosity of air in our particular case, but the kinematic viscosity of any fluid that you're working with. So, and all of this I'm going to be talking about Reynolds number at sea level. Now, conveniently, most of my testing is done at sea level, so I get to take the easy way out and just use the same kinematic viscosity all the time and say, hey, I was at sea level. So what these parameters bring together is the ratio of the inertial forces to the viscous forces. And that tells us about the ability of that fluid to stick to the surface of the wing. And what its conditions are when it's attached to the wing. Now, inertial has to do with speed, hence the velocity here. Now, that's mass, essentially mass times velocity. It's the ability of a certain mass of air to move forward. If it has high inertia, Newton's law, going to keep staying in motion unless there's something to resist that motion. So high inertia, if there's something resisting it, high inertia means that it has a better ability to move through against that resistance. And viscosity is, and this is the kinematic viscosity, the viscosity that's involved with the basic parameters of the fluid, and connected in with the velocity that it's moving at. So kinematic viscosity, for example, honey compared to air is very viscous. I might do a little clip here later where we run some honey down a curved spoon and some water, and we'll see the difference. But honey has a tendency to stick to the spoon. And you go, well, Raul, that's because honey's sticky. Well, no, there's a reason why it's sticky, a variety of reasons. But one of the reasons it's sticky is it's viscous. It's very viscous. It's thick. So it's going to have a tendency to stick to surfaces. The thinner you go, the less likely you are to stick to a surface. So air, very thin, not very viscous. And it will detach itself from the surface that it's flowing on quite easily. All you have to do is give it enough inertia, give it a shove, right? And if the surface curves, oh, the air is just going to go straight because there's not much in the way of kinematic viscosity to keep hold it to the surface. It's not viscous. It doesn't stick to the surface. And if you got enough inertia, off you go. Now, when that happens, when you get enough inertia, it begins to want to separate from the surface. The shear forces cause turbulence. As the flow begins to shear away from the surface, and I'll draw this later when I draw the boundary layers, that shearing forces pulls it off and the flow begins to turbulate. That is what is known as a turbulent boundary layer. Once there's turbulence, it becomes stickier. It'll hold to the surface better than laminar flow. So at the low end of Reynolds numbers, it's all laminar. And there's nothing you can do there's not much you can do to unstick it from the surface for a given velocity. And if you get at the higher speeds, you will have a higher Reynolds number. And at a certain point, up around, for airfoils, that's up around, where did I have it here? Up around 500,000, 550,000, you'll have turbulent boundary layer, and it will stay nicely attached to the airfoil. Now there's range between 100,000 and 500,000 on Reynolds number that not much is known about. That's because most aircraft do not fly in this region, and any aircraft that do fly in this region are relatively limited in their production number or usefulness to society, so nobody's ever really invested the money needed to go study and understand behavior at these Reynolds numbers on aircraft. Most of the aircraft that fly at these Reynolds numbers are human-powered aircraft and hang gliders. And there's really not a lot of money in either one of those, so the work never got done. And hang gliders have been developed experimentally over the years. It's not that they go do a bunch of very sophisticated computational fluid dynamics or other analysis, like even on the structural testing. You want to do structural testing on a hang glider, do you put sandbags on it? Do you build a big rig to bend it? No, they go stick it on a pole on top of a vehicle and they go racing 100 miles an hour down the runway and they put the nose down and they go, did it break? If it breaks, they make it stronger. Likewise with the aerodynamics. Well, this worked on the previous one. We made a little tweak. It didn't work, so back up and redo it again. So it's experimental process. And hang gliders have been developed that way for decades, and it's really pure engineering. There's not a lot of science in there. So there's been a little bit more science, but not like we used for developing regular aircraft. So not much is known about this Reynolds number region, other than it can be problematic. Because when you're in this region, you don't know, am I going to be laminar or am I going to be turbulent boundary layer? Because if it's laminar, I want a certain type of airfoil. I want to do certain things with that airfoil to make sure it works properly at those Reynolds numbers. Like I want low Reynolds numbers, I want thinner airfoil. I want it smooth. I want to try to keep that flow laminar. Turbulent boundary layer, standard airfoils. Pull them off the shelf, pull them out of a book. Everything's fine. In between, we get a phenomenon known as laminar separation bubble, and when I get back on the computer, I might talk about that directly. Maybe I'll stick up some photos here that show laminar separation bubbles and how they occur on the wing, and that's happens when you're in transition. When you're at a Reynolds number where you start out with laminar flow at the front of the wing, and it's moving along and it's speeding up. It's in its proverse pressure gradient going up to the highest spot on the airfoil. The flow is speeding up, pressures are dropping, everything's peachy, the flow is laminar, and all of a sudden it turns a corner and it's got to head back downhill, and that's what we call an adverse pressure gradient. And with laminar flows at certain Reynolds numbers ranges, when you do that, the flow will want to separate. The flow wants to go straight because the air is not viscous enough to stick to the surface, and it'll separate for a little bit. But the Reynolds numbers are really low. You don't generate a turbulent boundary layer, and no turbulent boundary layer, it's not really going to stick very good, and you get some vortices in there. And we've seen this on my wing. I might take a little aside here and run some video and show that type of separation on my wing in flight. And then it'll get past that spot and it'll reattach to the wing. It might come all the way back to here and then reattach, and you get some more laminar flow. And this laminar bubble that can form in like this region Oh, it can move around. It can go span-wise. It can go back this way. It can go back forward. Totally unpredictable. And not only that, it really wrecks your aerodynamics. And in my case, it's probably been impacting the control surfaces, and at various times I lose control of the aircraft. And that's bad because I prefer to be a pilot, not a spectator. Spectator's not very much fun when you're flying and you're the only person on board. Not fun. So, Reynolds number. Hard to understand and truly appreciate, but it is a key parameter in the performance of any aircraft. Now, one of the tricky things about the Reynolds number is L here, the characteristic length. And why is L in there? Now, L, this way, from the leading edge to the trailing edge, as it becomes larger, you get a higher Reynolds number. But what does that mean in terms of the flow? Well, we're going to discuss that later, and that's where things will get a little complicated, so I'm leaving it for later. But higher, if you're in a transition region where you're somewhere down around in 300,000 or 400,000 and you got problems, if you had more chord, you'd be above 500,000. You might not have any problems. You have turbulent boundary layer, and everybody's happy. That is not the case for my wing. My wing, this wing right here in front of us, its nominal tip chord is 24 inches. And its nominal Reynolds number associated with that is around 400,000. And that is really a problematic area. And for my patrons, I've pointed out, that's no man's land. We don't know very much about it. Nobody goes there. Nobody knows what's going on. Hang gliders, however, operate there a lot. So does my wing. And yes, going into this design, I knew it could be a problem. But I figured I'd set it up so that it's highly similar to my first wing, and that my controls were very effective. Everything would be fine. But it didn't work out that way. And it's going to be a bit of an explanation about why it didn't work out that way. But this L here is going to be very important to us in the future, and not just in terms of boosting the Reynolds number, but in terms of understanding the physical aspects, the physics of the flow, the fluid mechanics that are going on with these type of aircraft at these Reynolds numbers, and why certain things work and other things don't work. And how, of all things, as we have developed these high-performance, foot-launchable sailplanes, we accidentally, I don't know of anybody out there that's actually figured it out, realized it, wrote it up as a technical paper and published it, because if they had, I'd probably know about it, that explains what the heck's going on. And in the process of experimenting with these, and by the demands of the design, just by happenstance, we ended up at a workable solution for control surfaces. But not because we were operating at a real low Reynolds number. It was for other mechanical reasons, which I'll discuss later. So, the Reynolds number and L, the characteristic length, are going to be our friends as we go through this discussion. And I put a link in the description if you want to go understand, a couple of links, if you want to understand Reynolds number better. The one for sure is Wikipedia, but the math will burn your brain on that one, maybe right to the point of melting. It's been so many years for me, I can barely understand the math that's going on in there. And I'll try to find another link that's to a more practical explanation of Reynolds number. But if we remember, it's the inertial forces over the viscous, we're in good shape. It's the ability of the air to stick to the wing, or the tendency of the air to just go straight and separate from the wing and go do its own thing. Okay, so now that said, let's talk a little bit more. Okay, that said, I'm going to take a little break here, go get a beverage, and check and make sure the video is coming out okay, and then we'll come back out and we'll talk a little bit more about the Reynolds number issue and the design of my wing and how I ended up where I am. Okay, I am back after a little break to take a look at that, and I see that a couple of things. Charlie the Beagle is keeping up his standard of appearing in most of my videos when I least expect it. I hope you liked his little cameo walkthrough there. And sound's not the greatest, but then again, I'm not into this for strictly entertainment purposes. I'm doing this work so that I can spread knowledge and help other people out, and maybe at the very least a modicum of entertainment via distraction more than anything. But I hope you can bear with the sound. So all of that said, I ran out of battery power, so I had to go get power supply for the camera. In my recent research on Reynolds numbers, I found this handy dandy graphic. I'll try to hold this in a little closer here. I hope you can see it. At least you get an idea what it looks at. But I'm going to call this up on my computer and do voiceover and walk you through the graphic. But what it shows is the various regions of Reynolds numbers for various types of aircraft: insects, birds, UAVs, hang gliders, general aviation, and so forth. And I've plotted the Reynolds number performance of my wingtip on here so that you can see that I'm squarely within the region of hang gliders, as one would expect. You know, they all come out pretty much the same. So we'll go take a look at that a little closer, and then you'll come back and I'll talk some more.